Yeah. So our next meeting will be in September in Netflix, and the next will be in October, either in eBay or Box again, and the next, like the opposite, Box or eBay. So that's the future.
Thank you. Okay, so thank you all for coming. I'm going to talk about what do specialization, value classes, what unboxing have in common. Before I go on and start talking, maybe it's good to present myself. I'm a PhD student in Martin Maderski's lab. We call it the Scala team at EPFL. You probably know me as the Miniboxing guy. I always develop on this little plugin that I like for specialization, and yeah, that got me the name. But I also worked on specialization, on the back end, on Scala Doc, if you know diagrams in Scala Doc. That was a project by a student who I supervised. If you like them, I hope you like them. Okay, I put the Twitter handle and GitHub and all that. Okay, so let's get to the talk. What do auto unboxing, specialization, and value classes have in common? Well, first of all, what are they? I'm sure you all know, but maybe presented from a certain perspective, it'll become more and more clear. Okay, so auto unboxing. Let's say we have this method. I always like to use identity because it's very, very simple and it's generic. So when you run it when you compile it with Java C or Scala C, what you get is basically another method which takes an object, returns an object. And this is a process called erasure. It's the simplest way to actually transform generics into bytecode. There are, of course, others. Maybe .NET programmers here will say .NET is much better. It probably is, but it made other, in terms of performance, but it made other trade-offs that made log them in other directions. Their type system cannot evolve without the virtual machine. So let's take identity of 5. That's running identity on executing with parameter 5, and we get that compiled with Scala C. Well, this is what you get. I guess everybody in the room got that and hates it. This basically uses the Java long integer, which is the object representation for the integer 5, and then it unboxes it using int value. So basically what this does is inflate the requirements on the heap, because you allocate a object header on the heap. That's pretty annoying. And then it also creates garbage which you need to collect that pauses your program in the middle of execution. It's indirect addressing, because you don't address the value directly. You don't get the value directly. You have to go through a pointer to some offset and read it from there. And finally, it breaks all guarantees about locality. So if you have an array of integers, of unboxed integers, you have a guarantee that they will be one after the other in the memory, so you can get them in a cache line. Whereas if you have an array of boxed integers, well, they're pointers. They could potentially point to any place in the heap, not necessarily local. So this is pretty bad. What does Scala do about it? Well, when you compile something like 5, val5 of type int, well, it does auto unboxing. Well, maybe it's good to say that Scala int behaves much like an object. So it can go into generics, it has methods, so it looks like an object, right? What Scala C does is actually unbox it. So whenever possible, even though in Scala everything, all the integers look like as if they're objects, they're not. The compiler does this for you. And you have an unboxed integer. If you have 5 plus 3, it will of course get also unboxed, 5 plus 3 with an unboxed addition. So this is pretty good. This is very good. Now when you interact with generics, what you get is basically Scala C again will rewrite, again it will try to unbox 5, but the call will get boxed because identity does not have, it is generic and does not have a version that will work with unboxed values. But it does this boxing coercion, so basically transforming from one representation, the unboxed representation, to the boxed one automatically. You don't have to think about it, it just does it. It's very good for some people, it's annoying other people because somehow the compiler introduces boxing operations in their code. So, but it's a trade-off. It makes things simple from a programmer's perspective. And we have, at the end, we have also the unboxing coercion, which takes an object, an integer, and extracts the value. Okay, so far so good. But if we think about at the higher level, if we think about Scala int, what is Scala int? Well, it's two things, right? It's the unboxed int, which we like, and it provides us fast operations, and at the same time is Java-lang integer. And this Java-lang integer provides compatibility with generics. That's the only reason we use it. But the two of them are incompatible. So you have coercions going from one to the other and back. And that's very important. The compiler takes care of that. Now that we know what autoboxing is, let's look at specialization. Specialization, again, I come up with this example over and over again. Through specialization, we not only get one method that takes the object and returns an object, the erased version of the method, but also get other variants. For example, for booleans or for characters, we get different variants. All of them take the unboxed parameter, return it unboxed, which is great, but we get about 10 versions of them, which, okay, we could live with that, no problem. And if we have identity of 5, what this compiles to, well, just taking the specialized variant for integers and call it on a 5. And it's perfect, works wonders. There's no boxing. What if we take this method tuple, which takes 2 type parameters, 2 arguments, each of them with a type? Well, for specialization, we get 100 methods. So that's already a bit too much. But if we had 3 type parameters, that would be 1,000 versions of the method. So no, we need to do something about it. And this is where my project comes in. That's me smiling there. Well, Miniboxing takes a different approach to specialization. And instead of having having 10 versions of the code, you still have one that's erased, that's used for objects, and the other one uses a long and encompasses all the primitive types. So there's no need to actually have 10 versions. And when you have n type parameters, you get 2 to the power of n methods or classes. Well, now in the current version it's 3 to the power of n, but let's stick to 2 to the power of n because it sounds better. Okay, so identity of 3 with Miniboxing. No surprise here, it gets redirected to the version that is mini-boxed, and you have a coercion in there, int to mini-box. Okay, if we think about mini-boxing then, what we have is a generic type parameter t, right? Which again splits up in two versions. It's long on one side, the encoded version, which is the one we like, and t, which is erased to object, the generic one, which gives us the compatibility. Compatibility with what? With other erased generics, with method calls, with super types, and all kinds of other features of the language. Again, they're incompatible. Oh, yeah, and we have to introduce coercions. So there it starts to look similar, right? Let's see value classes. Value classes, like the usual request, everybody requests, give us a complex with two doubles that you unbox. This is very, very common to have this request. Through a value class transformation, what this will get transformed to is, this is a method that will return the value, the real value of the complex. So what it would return is, well, how it would get compiled. Well, on one side we have the value class, but the compiled version just takes the real part and the imaginary part. There is no need to create an object. Why bother creating an object when you can inline basically the fields there? Let's take another example. You do create a value with complex, you do the value class transformation. Well, no surprise here, the value gets exploded, split up into its fields, and each of them gets the value. So far, so good. Again, no object created. But now, what if we of course, all the classes in Scala, everything in Scala is a subtype of any. So we can assign a complex class, an instance of a complex class to an any. So how does this get translated? Well, just box it. That's the way we know how to do it. And if you think about boxing, it's again a coercion, right? So it's basically a coercion that converts the split up fields into something that is of the other, of the box type. So value classes, again, we start from a value class, the high level concept, which we split up into the structure or exploded fields, or into the class, which is by reference, passed by reference. And again, we see the same pattern. They're incompatible and they need coercions. So there's certainly some similarity in there, right? At this point, we kind of see it. Okay, so we saw all of them. We haven't seen multi-stage programming, but I think for now let's leave it aside, because multi-stage programming would take way too long to describe and to get an idea of it. But it's also included in that list. Okay, so let's try to answer this question. What do they have in common? Looking at autoboxing, at miniboxing and specialization, value classes, look very much alike, right? So starting from a high-level concept, we first of all split it up into different representations. So this concept is presented to the programmer as a one entity, but in the end, after the transformations, there are multiple versions, multiple representations for that. And it's each of the representations fills up a certain compatibility requirement. Like with generics, with methods, that's something that's important, because we're in a language. The language has multiple features. So each representation has a feature that it will interact well with, and some with which it won't interact at all. And then we introduce the necessary coercions between the representations. Okay, so that's the first time you'll get to see the outline. We talked about what is uniting, what is the common theme of these transformations. Now, let's take some time to think about why is this important. Okay, so the reason I present you this is because there's a transformation we call the late data layout transformation. And it's basically exactly what we've seen, a concept, a high-level concept that goes into multiple representations, can be split up. And it takes all kinds of, it's based on all kinds of constraints. The constraints can be generics, erased generics, could be methods that we call through dynamic dispatch, could be subtyping, could be domain-specific information based on what we know about purity or about DSL elements. For example, multi-staging doesn't even care about generics or their implementation. It's all about the DSL semantics there. And what I've seen is that this pattern is recurrent, appears in many, many situations. It might just be the fact that I'm working with this, and when you have a hammer, everything looks like a nail, but it fits so well on so many use cases that I'd like to basically get people to show me other examples and see if actually, am I the only one who's seeing this as something general that works in very something fundamental. So the areas I've seen this pattern are unboxing, specialization, but even in different situations on multi-stage programming, function representations, the way we represent closures, the way we use data structures. And this is actually very interesting. So if you take the concept to be a list, and then it would have two representations, right? It could have the lazy list, or maybe a stream, or the actual list. And when you have comprehensions with pure functions, you could use streams. That would not be incorrect. As soon as you have something that's impure, where you need to actually run the closure and execute it for each element, you can switch back to lists. There's no problem. And again, they're incompatible. You wouldn't have, a list cannot pose as a stream, and a stream cannot pose as a list. Therefore, you would need to have some constraint coercions inserted. So for example, one thing that I thought, let's take this code with a list of 1, 2, 3, a very simple list, 3 elements, and then map and filter, right? In this code, after the map, you need to materialize the list. And depending on your code, C, the original list, might become garbage. So it will not be necessary anymore. And, I'm sorry, after the filter, you will need to materialize once again, creating more garbage. And this doesn't, it could be avoided very well. For example, if you replace C by a string, knowing that the closures are pure, the functions are pure, and again replace D by a stream, well, you wouldn't have any materialization, any garbage at all. So you get away basically with mapping and filtering for free. Well, not for free, but at least without garbage and overhead. So again, now I'll try to ask you, what do you see as a use case for this? So I showed you a couple of examples that I have thought for it, but I think it's interesting, maybe not now immediately, but tell me what are the use cases in your code. You're professional developers, so I don't get to see the code. I get to see the compiler, the backend, and all that. But in the real world, what are the transformations you would benefit from? Again, the same rule, concept and different representations. And this way I could validate, on your side you could get your use case solved, and I could see if, hey, is this thing actually going to fly? And It might not be a perfect fit, that's not a problem. But it would be good to validate it and see if there's a chance it could work. Okay, so we've seen why this is important, or at least why I perceive it as being important. Let's go through the transformation a little bit. How do we transform a program? And I think that if you know what transformations are happening, what is happening in the program, you will actually know whether your use case could fit the transformation. And you will use auto unboxing as the running example, because this is something we already know we all had problems with, so it's just very, very easy to reason about. Again, that slide just shows the idea. And by the way, coercions are important. Let's see. We start off with a naive transformation. This is just replacing the representation. So from a code like this, where you have a list of integers, you take the head of it, and then you store it in X, and then create Y, which is another list of integers, just based on X, the integer obtained before. With a naive unboxing scheme, you just transform X into an unboxed integer. What would this produce? Well, there would be a mismatch. In one place, you would expect to have an unboxed integer returned. Actually, it would return a boxed integer. On the other hand, you would have another representation mismatch when creating the list, because the list expects boxed integers, and you give it an unboxed integer. Okay, so naively replacing the representation won't fly. So it creates mismatches, representation mismatches, and we could compile it down to bytecode. But it will just crash the program with a VM error saying, no, you cannot assign a reference to an integer. I won't let you do that, for good reason. So we need coercions. Whether we like it or not, we need coercions. And one way to introduce coercions is the syntax-based transformation. A syntax-based transformation basically has a very simple way to apply. Basically, whenever we transform a value, we also coerce its definition. So we unbox, for example, a value, we also unbox its right-hand side. And every place where this integer is used, we need to replace it by box of that integer. So let's see this in practice. Okay. So for example, let's take this example, the first line from the previous example. So we just unbox X, and the right-hand side also gets a coercion, an unbox coercion. So far so good. There are no references to X in the code, and that's all the transformation we need to do. Great. Now let's take Y. Y this time is not creating a list, but just taking this X we had before and copying it to Y. Oh, I'm sorry. Okay. So let's transform one by one. Let's not transform X and Y at the same time. First one will take X. It will become int unbox like we've seen before. Y, on the other hand, gets box because we switched X from box to unbox. Every reference to X needs to become box of X. So far so good. Let's see the next transformation. Okay, so we try to transform it. What will we get here? Remember that we need to unbox to coerce the right-hand side. Unbox of box of X. Well, isn't that stupid? So we take an integer, we box it, and we unbox it. Luckily, the Java virtual machine is smart enough, at least Hotspot is very smart, about reducing such stupid mistakes. but we shouldn't make it in the first place, right? Okay, suboptimal. We could have a peephole optimization to solve that. It would just say, well, whenever you encounter unbox of box of something, make that something directly redirect to that something. And the other way around, box of unbox. Okay, so that would do the trick. We would get the example solved by this peephole optimization. Okay, fine, let's include a peephole optimization in the pipeline. It's not going to kill us. Let's take another example now. A method takes two integers, rolls the dice, and returns one of them. Again, very simple things. We don't want to get into complicated code. I can assure you that these things scale when I tell you they scale, and they don't scale when I tell you they don't scale. So, again, transform one by one. We make T1 an unboxed integer, and we get a box of T1. Same for T2. Is there anything missing in this example? Anyone? The return type. Right. So, we need to unbox the return type. When we unbox the return type, we get an unbox, ugly unbox slapped around the entire if expression, which is again suboptimal. We take two unboxed integers, then we box them and unbox the result. And this time our peephole optimization won't help us because it recognizes unbox of box of t, but doesn't know anything about unbox of if, right? We have to teach it. Okay, new peephole rule. Fine. Sync outside coercions into the if branches. Namely, take that unbox and put it on each of the branches. Good, so far so good. Then it has a rule, a nice rule, which says, okay, unbox of box of t is t. Good, we have the example. But it's complicated, right? I mean, we had to go through introduce coercion, then take it out, then move it, then all that. That is usually expensive. From a compiler's point of view, traversing the tree multiple times is inefficient, right? And then there are other problems. The fact that it needs not one, but multiple rules for each node. How to, in the tree, each term in the tree needs to have special rules for this syntax propagation, for this coercion propagation. This is something we don't want. And it needs this successive rewriting, which again we hate. And finally, it's impossible to guarantee optimality. So I actually had this implemented for the Miniboxing plugin last year, and I was going crazy. I thought I optimized all the possible code patterns, and then something would pop up and show me that there was one rule that I forgot to consider, and I need to do that one too. And then I came to this conclusion that a type-based transformation might actually help. The main insight of a type-driven transformation is that we give this representation information to the type system. So we propagate this information in the type system and let it reason about, let the type system reason about representations. So all we need to do is make it explicit. Okay, and then what happens is that retype checking the tree, so giving it back to the type checker and saying, okay, check it again, tell me where you find errors, actually helps us introduce coercions. Wherever there's a mismatch, we know there's a coercion that needs to be inserted, because the tree before originally passed through the type checker was okay, and then we made this choice of splitting things up, and then it started being having mismatches, representation mismatches that translate into type mismatches. So far, so good. Now let's come up with a recipe. 3-stage mechanism. First of all, we basically inject the representations in the tree. We mark those values, some values in the tree according to some rules that satisfy the constraints given by the language features allow us to mark those values that we want unboxed wherever possible. And then we introduce another phase, which is called coerce, which just introduces markers for coercions. What this means is not coercions yet, but just some information, some snippets of information that there will be a coercion there. Finally, the commit phase translates the tree from something that has markers and annotated types that will become new representations to the actual representations, to the actual coercions. Okay, so let's see this in practice. Before we see this in practice, I have to warn you. The way I write in all the descriptions I write, and even in this presentation, I always write the annotations before the type. This is not according to Scala syntax. In the Scala syntax, you would write int unboxed. So you would first put the int and then the unboxed. I find it much more natural to say unboxed int, because I can just read it, it's an unboxed int. Great. Why bother to say int unboxed? Okay, so when you're writing code, you will have to switch the two. Okay, we have in the corner the three phases. Let's take the choice example that we had before. We know it can be translated to something that has no coercions. Let's see if the type-driven transformation can also do that. First of all, we get to the inject phase, which will annotate the values that gets unboxed. How does it do it? Well, introduces annotated types. Just puts an unboxed in front of the int. Well, from the perspective of the compiler, it's a bit more complicated, but this is the fundamental idea. And this is a configurable step. It can, for example, you can choose, okay, I want to unbox T1 but not T2, or I want to unbox the result or not, up to the transformation at hand. Then it passes the tree to the coerce phase. As we said before, the coerce phase just takes the tree and retype checks it. Well, what does it mean? First, it starts from the top. In this case, the method tries to retype check it. How to retype check a method? Well, you need to look at the arguments, and you need to look at the right-hand side and make sure the right-hand side coincides with the declared return type. This is, by the way, so it looks at the right-hand side, which is the if expression. The method promises to return an unboxed int. If you used implicit conversions, you know that if it does not correspond, it will trigger an implicit conversion. And how does this happen? Well, the compiler records the fact that it needs to return an unboxed integer as the expected type. And this is part of local type inference, which is much more complicated than just the expected type. And local type inference is the tool, the feature that allows you to write, for example, val x equals 3, and allows you to write even very complex expressions without putting the type. It's the inferencer. But we just use the expected type for now. It's enough for our purpose. So we try to type check the if expression, knowing that it should return an unboxed int. How do we do that? Well, we check the condition. It has to be a boolean. I'm not going into boolean, how to unbox booleans. I'm just talking about integers now, just to keep it simple. So it matches. It expects a boolean, it got a boolean. Now, T1. It should return an unboxed int, which is propagated from outside, from the if expression. And of course it matches, because T1 was unboxed int, and the result was, the expected type was unboxed. Same for T2. Okay, great. Next phase. We got away without introducing any coercions. In the commit phase, well, it does a very simple thing. It replaces unboxed int by int. We won't go into replacing int Scala int by Java lang integers, because That's just plain simple. There's nothing fancy about it. And it will give the final semantics to the coercions, creating a boxed integer and extracting the unboxed integer. Okay, so this is how it looks like. Do you remember from the syntax-driven transformation how many steps it took, how many transformations it took to actually get to this code? Okay, that's it. Good. So let's go once again. The three-stage mechanism was something that added annotations in a very, very flexible way, selective way, and then added coercions based on the type checker, on retype checking the tree. Finally, it's committed to a certain representation, to a final representation. Okay, so this is already done in Scala C's erasure. And it's a very similar transformation happening there. Unfortunately, it's a little bit less flexible because it does not allow annotating the specific values that you want unboxed, and it's entangled with other transformations, so it's not really usable. So what we did was take this transformation, which was already there, make it more general, and thus allow it to be used for more use cases. So why do this? Well, it was useful for miniboxing in the first place. That was my number one concern. And then we were able to do other use case with it, to cover other use cases with it, like value classes, multi-stage programming, and hopefully your transformation will also be covered. Probably that's the most important one, so please pick up when you have ideas of what to do. Okay, so based on this type-driven transformation, let's see some of its properties, right? The three of them I highlight here are consistency, selectivity, and optimality, which, by the way, we did not yet prove formally, so it should be proven formally to state it, but we have reasons to believe this is optimal in the way it translates the code. So consistency. Well, we just push all the representation information in the type system and let the type system figure it out. Well, having that representation information explicit allows the type checker to make sure that we don't do mistakes. So anything that we do, as long as it's verified, what is a type checker in the end? It's a program verification step, according to some type-based algebra, to the algebra given by the types. Therefore, adding more information to this algebra allows the type system to verify more properties of our program, including representation information. Okay, so mismatches lead to coercions. It's very simple. Whenever something doesn't fit, we make it, patch it so that it fits. And this can be done regardless of the representation. There's no real need to give semantics to this coercion. We know we need to coerce between two representations at the meta level. And then in the commit phase, you can see this happens in the coerce phase. But in the commit phase, it's then only then that we actually care about what exactly happens, what is the final representation, and what are the coercions. Selectivity. Well, annotations allow us to pick the exact values that we want to unbox, that we want to transform. So, for example, value classes, we had the problem with value classes that the Java virtual machine does not allow multi-slot return. So we cannot, for example, in the example of complex, return two doubles from a method. We can only return one stack slot. So the way we handle that is by adding a simple rule. If the value class has multiple parameters and it's in return position, don't mark it. That's it. Don't annotate it, and it works. Bridge methods. Same. Bridge methods, some elements need to be annotated, others not. No problem. Just annotate what's necessary. Staging, I'm not even going there. It's completely domain specific. It doesn't have anything to do with erased generics. You can have, for example, a list of staged int. That's completely orthogonal to erasure. So the rules are completely different, and staging gives domain-specific semantics. So to show this selectivity and how simple it is to use it, well, let's assume we have some transformation that doesn't want to annotate the first parameter t1. It annotates t2 and the result type. Well, this happens at the inject phase. At the coerce phase, we get to retype check the if expression with the usual unboxed int, the expected type unboxed int taken from the method. So far, so good. Well, retype check t1, and there's a mismatch. What does it mean? Coercion. No problem. Unbox t1. That's it. We get to the commit phase, and it just commits to the final unboxed representation. No fancy problem, no peephole optimization, no rewriting, and all that. Great, optimality. So, choice again. We take the same example as before. T1 is boxed this time. And what do we see here? There would be two ways to transform this code. You could either unbox T1 or box T2 and unbox the if expression. The fact that the type system propagates expected type through any node, which I call transparent, like an if expression. The if expression just says anything that I'm constrained to, I constrain my branches. So it's transparent. It just moves the problem away. Just puts the constraints moves the constraints deeper. The fact that we have this, it will mean that every time a coercion is inserted, it's inserted as deep as possible in the tree, making it, basically executing it as late as possible, only when it's really necessary. Let's see some use cases now. So I hope I convinced you the transformation has these three properties. For miniboxing, if we try to use it, let's see again the tuple method. And the one that was making 100 versions of the tuple method in specialization. With miniboxing, the way you translate it, you would first duplicate the body. Take the tuple and do 4 copies of it. And you have some leading arguments. I'm not going to talk about it. They are tags for the people who use miniboxing already. But let's not talk about these. We'll have 4 versions of the method. Where one type parameter is boxed, 2 versions for the other one, boxed and unboxed, and again, basically the Cartesian product. And what we get there is we start off by having these T1, T2 without any annotations and everything as simple as possible. And the second part is adapting it. To adapt it, what we do is annotate. I put a @long annotation. It's not technically the same thing. In the Miniboxing plugin, it would be called @storage of long. But the point is, we annotate those values that change the type. And we use the transformation inside the body. And the body gets adapted. And that's all there is to do. Create several methods, use a transformation on them, the bodies get transformed in a consistent and optimal way, and then we can rewire, knowing we have different versions of the method, to the most specific one. For example, if we had tupled of 5 and 5, 2 integers, we would just use the tupled mm, which is the specialized one for our use case. Okay, value classes. Value classes, I'm going to talk about one of the examples I gave in the introduction, because all of them are pretty much the same. There's no real difference. But the point is, during the commit phase, this time it happens during the commit phase, we know, for example, in the ABS method, that C is an unboxed complex. So how do we translate it? We just split up the fields. That's all. There is no fundamental problem with the fact that we just explode the parameters into two of them, and at the use site, when we call apps, it will just split up the value that it finds there. Okay, great. So I'm not talking about all the details. Of course, there are details, exceptions, different problems that we encountered during this transformation, but I'm not going to talk about the details. The idea is pretty pure. And actually, it's Eugene, the guy who does macros in Scala, who implemented this. He started off hating it, hating that I asked him to do that. And after 2 weeks, a week and a half, it took him to implement value classes using this translation. He was loving it. I'll let him talk about it. I have to thank him for doing that. He knows all the details. I mean, much better than I do. Okay, multi-stage programming, another use case. Well, we won't go into this today because it's, again, too much. Okay, so we talked about a transformation. Let me give you a brief benchmark for just to whet the appetite of those people who really need to see numbers, right? It's going to be also, I presented an earlier version of this benchmark for the Scala Days conference, but it's slightly evolved, and I'll explain why. So it's done on the Scala library. It's a mock-up of the Scala collection immutable list, and we just take the least squares method that basically fits a set of data, a set of points with a straight line. Okay, we'll wait a minute. Okay, this is joint work with Emery Janet, who's a student in EPFL. I'm really grateful for all the work he did. He presented at the Scala workshop a few days ago. And he prepared a mock-up of the Scala linked list with tuples, traversable like, seek, iterable, all the things that you hate about the Scala collections that are really hard to grasp and never seem to make sense. He had them there. And then, based on this, he mini-boxed the set of his mock-up of the linked list. And FunctionX has a very nice story. This is a new addition to the Miniboxing plugin. It happens, I think, 3 weeks ago. So FunctionX, as the story goes, is specialized. Miniboxing and specialization have a common denominator, the boxed value. They will be able to talk to each other, they will communicate, great, all that is good, but they won't be able to communicate from miniboxing directly to a specialized method. They will go through boxing, which is pretty bad and kills performance. So one way to do it is the way we do right now, is automatically create a minibox function 1, function 2, whatever, and automatically the plugin rewires any function that you create, any function x, to a minibox function x. And it's another LDL cycle. So again, maybe when all you have is a hammer, you see everything like a nail. But it worked wonders. So it seems to work, and it's fully automatic. The other version we benchmarked is what Emmerich did. He just created a myFunctionX, which was miniboxed. And he didn't have the nice syntax which said x goes to x plus 1. He had to basically desugar, as if he was the compiler, to an anonymous class that conforms to this function minibox, myFunctionX. Wasn't too bad, but he had to add this by hand. Okay, sorry. The benchmarks are here. So with my function x is the lightest one. You can see here I'm measuring time. So the time it took for the data set size. So 2 is 2 million elements. And I'm counting the overall time it took for the benchmark. Lower is better, of course. This is the one did by the benchmark Emeric did. And you can see it's the best one here. And there's also the one done automatically, which is not as good. I know where the technical problem is. It's just a matter of putting enough energy in fixing the bug. And I think I could lower this to the same level as Emeric's code. And then there's generic, which is pretty bad. So we get 30% to 45% speed up on a non-contiguous data structure. Of course, if you went on the website, you've seen the array buffer, which is contiguous. It can get 10x speedups. But even a linked list can get huge speedups when GC actually comes into play. So this is another benchmark. It's the same benchmark that we ran for huge collections, up to 6 million elements. And when the data set is large, we can get 3x, 4x faster just by the fact that we allocate things better. Fortunately, specialization here didn't create correct code, so the times flew through the ceiling. So I don't have it here, but it will probably be a bit better than Miniboxing if everything went well. Okay, so we talked about the benchmark. Let's see some conclusions, and then we'll do questions. And later I have a little surprise for you after the questions. So conclusions. LDL is a transformation. It looks like it's very general. It looks like it covers a broad range of cases. I'd like to hear what would be interesting for you to cover with this transformation. And I have to thank a lot of people, including Vlad, who organized the meetup, and all the people who helped out and tried the Miniboxing plugin, provided feedback. So please, please, please do try it. Let me know if it worked, if it did not work, what did not work, and I'll be happy to solve all problems to make it work well. Okay, so I'll leave this slide and thank you very much. I'll take all the any questions you have. Yes?
So when you were doing your benchmarking, why did you have to rewrite the collection class instead of just recompiling the existing code?
What? Maybe I don't understand.
When you were doing your benchmarking and you were talking about the list,
Yes.
or it was a mutable list or something that it sounded like you had to recreate it.
Right. Good question. So the problem is the Scala collections are pretty big, and trying to mini-box them all at the same time would probably lead to some things that we overlooked and we're not compiling correctly. So specialization, not even for this simple example, for this slice of the collections, did not compile well. And the strategy is, instead of going for the whole set of collections, the strategy is to divide them in slices, try them out, make sure all the code is correct, and then once we have certain slices that we trust will work well, we can go for the entire library.
Thanks.
Hi, thanks for the talk. Do you think that this approach would work for whole program specialization? And I'm thinking in particular if you're using the cake pattern and you have some abstract type that eventually gets implemented as a value class or as a primitive type, could you apply this transformation to rewrite a concrete cake to kind of push to propagate that specialization through the whole implementation?
So right now, when you have a cake batter and you have traits that you mix in, if the traits are annotated with the mini-boxing annotation, they will get you will get the optimized patterns. Now the problem would be, can you actually, given a class that's annotated, make sure all its traits, all its super traits, super classes and parents are annotated with mini-boxing? Sure, you could. If you do a whole program compilation, you could do an analysis phase before and say either do it directly, just annotate them directly, or report to the user, and you have this trait that is not marked as mini-box. This is actually something that I'll implement within the next probably 2 weeks, because it's something that I got a second request. This is the second time I get a request for it. So
great. I'll play around with it too.
Okay, thanks a lot.
So suppose we start using this thing. What would be an impact on like development tools like IntelliJ, for instance, or Eclipse plugin? The plugins don't understand this stuff, right?
So yes, there might be a problem when you're interacting with Java, because Java does not know the semantic information that something is generated as an artifact of the Scala compiler. But for the IntelliJ and for Eclipse plugins, they only run up to the typer phase. So they only type check the code, and from there they extract all the information they need, including the expansions of macros. Therefore, there's absolutely no reason they would be affected by the further transformations later coming in the backend. Only the bytecode that they generate on the disk would be changed, and therefore a naive Java tool would pick it up, and you would see strange names like you see in stack traces right now with $MCI, $SP. But that would be the only artifact. Of course, you would break reflection, because if you assume classes always get replaced by something else, and you would get this stack trace method.
I'm curious, you made that third step commit. Is the implication there is sometimes it fails? Is the idea is you run this and occasionally you just have to back out because the typer is unable to solve the problem?
It's not this reason I called it commit. It's the reason I called it commit is because it's only then that you actually need to commit to the final representation. Whereas, the rest of the algorithm, the inject phase and the coerce phase, are pretty general. They're agnostic to the actual representation, to the number of representations, to the semantics of the representation. It's basically separating concerns. In the beginning, you do the semantic level, and then you do the actual planning in the commit phase.
Again, I could be missing it, but for unboxing, I can see that I can easily see that there won't be a situation where it can't coerce it to a successful value. But maybe with some of the other applications, is it possible that literally it could try to propagate and find it can simply not do the conversion?
Yes, there would be cases like that. For example, when you would annotate a return type of a multi-param value class with a multi-parameter value class, you would annotate it as unboxed. Then you would end up in the commit phase. You would look at the code and, hey, this has no semantic equivalent. But the right way to fix that is go to the inject phase and say, don't annotate that, because I have no idea how to translate it back in the commit phase.
So that does suggest if someone wants to make use of this mechanism, if they want to add a new plugin to use LDL, one thing they'll have to consider is sort of the completeness of their coercion, and then they may have to realize, oh, I'm going to have to put constraints on my injector to make sure I won't fail in the later phase.
Exactly. Yes, this would be the typical workflow. You start with annotating anything, and then you see which things have no equivalent later. But to be honest, I wouldn't expect a user just going into the repository, cloning Miniboxing and starting using LDL. I think as a compiler developer, I would do that, and I would already know what are the things that I just cannot do. And then I would instruct the inject phase to annotate the tree in such a way that it does not lead to expressions that I cannot translate. Furthermore, there's with the value classes plugin, we had the situations where we did not know how to translate even an expression that looked like correct. For example, what would you do if the result of an if expression was marked as minibox, as the unboxed value class, multi-param value class? You cannot put, theoretically, you could put multiple fields, exploded fields in the backend on the stack. It's okay. But at the high level we're doing this transformation, you just couldn't express that. So Eugene asked me, hey, look, have something that will recognize this expression in the coerce phase, and the coerce phase, if it encounters this pattern that we cannot translate, just backs off and says, okay, in this case, we unboxed at an early stage, we unboxed the result of the if expression, and the values that the if expression returns are boxed. So it's basically a cooperation between the three phases.
So I'm curious, one last question. How expensive is having to sort of redo the typing and coercion? You're going through the sort of typing coercion phase again, right? Because you're doing it much later in the compile cycle, I assume. What's it add to sort of the compile time?
I haven't measured it precisely. I'm also interested. It doesn't look like it's something that should take too long, because it's a lot less work that the typer is doing compared to what it's doing in the beginning when it's first type checking the program. To give you some intuition, everything related to name resolution is also done during type checking. And therefore you have all kinds of interactions, some things happening, some control going to another part of the tree, retype checking something else that's needed, and all this going back and forth with basically with continuations that are done through lazy types. It's pretty expensive. Whereas what we do and also type inference itself is very expensive. What we do instead is very lightweight, very simple. It just incurs a big switch which says, if that's a node which looks like that, do this. If it's a node that looks like the other thing, do that. This is the only part of the typer that we're exercising. I don't have exact, precise numbers. I will post them as soon as I have them.
I think right now the way you would do reflection on a generic function is type tags, right? Can you give us an idea what would be the interaction between using type tags and miniboxing?
Right. So using type tags, you would not get any. The fact that you use miniboxing would not affect Scala reflection. Type tags are generated early in the compiler front end during typer and are expanded and have all the information set. Furthermore, when it needs to load something from the disk, information about the class, Scala reflection takes information stored in the class file by a phase called pickler. The pickler stores all the information, symbols, signatures, and all that in the class file. Well, the good thing is Pickler runs before the transformation. So as far as Pickler is concerned, the signatures are very simple, the ones with @Miniboxed, not the ones transformed. So Scala reflection is not affected. Instead, Java reflection would get affected because Java reflection is not capable of reasoning about these artifacts. Scala is not really capable of reading the information pickled about each class. So you would get mangled names and mangled methods and all that. Okay, no more questions? Okay, so I wanted to surprise you with something. And there's always this thing that we work in the lab there and nobody knows what we're working on. So I try to round up all the projects and give a few names and a few pointers in case you're interested to follow up with a project that's in the lab. So what I'll start in a pretty random order in the office, the order in which offices are across the hallway. So don't take it as anything special. It's just random how I thought about them. I might have also forgotten. I apologize to my colleagues if I forgot an important project. So let's start with dependent object types, the dot calculus. That's Nada and TR who are working. It's the core type system for Dotty compiler, which basically is an experiment to see how much of Scala could be ported over to this cleaner type system. It's much cleaner in the sense that, for example, existentials that are unsound and have different problems in the compiler are not necessary in the dot calculus. Okay, so we've got 2 pointers there. Then pickling and spores. That's the work of Heather Miller. It's support for distributed programming. Picklers is a serialization framework which is much faster than the current state-of-the-art serialization frameworks in Java. So this is great. And you can see, you can learn more from the project websites, and Heather does some really, really nice presentations. Look on Speaker Deck and you'll find her presentations and you'll love them. Then Yin-Yang, this is the work of Voin and Sandro. It's basically multi-stage programming done with macros. Macros are a meta-programming mechanism that can be used to do multi-stage. And it's kind of a replacement for Scala virtualized, if you will. It's not necessarily complete replacement. Actually, it tries to be a complete replacement. Okay, so Scala.js backend. That's the work of Sebastian and Tawaz. It's basically compiling Scala to JavaScript. And it's much more than that. I mean, they're working on all kinds of crazy things. So I expect cool things coming out. The website is there, scalajs.org. Stage parser combinators. That's Manohar, another colleague. And basically, if you use parsers, they give you a very, very nice interface to specify a grammar. But they're pretty slow. They create objects all every time, and their performance is kind of lacking. So what he does is use staging, multi-stage programming, to optimize these to almost like the speed of a compiled regex. Okay, Scala meta. Oh wow, much meta. So if any of you have seen Eugene's presentation, you will know the image. If not, please go to the Scala to parties and look at the Scala presentation he did. Very, very nice. And it's a project about improving reflection, making it safe, completely changing the representation you have for reflection right now. Okay, Miniboxing, you know that. Scala Dino. Scala Dino is a project of a student. He worked on basically giving Scala more dynamic language look and feel. And actually it's pretty cool because it can compile, it gets Scala to compile programs that it would otherwise reject. So for example, you pass a string for an integer. Normally Scala would reject this program. Well, now it compiles it, and if you happen to run this path in the program where you did something wrong, it will bail out with an exception saying, sorry, this is a compile time error you did back when you compiled, and tough luck. Much like Python would with a runtime error. Okay. Sorry?
Why?
Why? Good question. It's an experiment. I mean, we do research, right? We can afford to fool around. And the idea was that when you want to, for example, focus on a path in the program, you refactor something and you experiment, you don't want to maintain a consistency of the whole code base. And sometimes refactoring tools do well for Scala, sometimes they trash your code beyond repair. So rather than having that, just focus on a critical path you want through the program and fix the others later. You still get, instead of compiler errors, you get compiler warnings. So you still get all the information necessary.
Do you do the opposite for Python then?
Sorry?
Do you do the opposite for Python?
People have tried.
No fun.
Okay. No, there are certain programming patterns like monkey patching that you just cannot reason about. So it's, I would say it's almost hopeless to try. But then again, I'd love to have somebody prove me wrong and design a type system that can accommodate that. Scala Blitz, it's an optimization framework. It's very popular because you just add a macro, add a scope optimized around a code that where you use collections, and it will magically transform into super optimized while loops that don't create any garbage and do the right thing. So it has a website, you can see it there. Type debugger for Scala, that's a very interesting project by Hubert. When you have some code that produces a type error, sometimes this type error, as you've seen for the LDL transformation, is not local there. It's some kind of interaction, long interaction between some type that was specified somewhere, some other type that was specified somewhere else, and they somehow, during local type inference, combined to produce a type error. Well, with a type debugger, you can actually say, hey, which nodes are the root causes that produce this error? Scala meter is our Google caliper. It's basically allows benchmarking, but with all kinds of nice showing ways to display results and to throw away if garbage collection occurred during a benchmark. Put it aside, it might not be the best thing to include it in the measurements, and many features to allow you to benchmark your code. Okay, the new Scala C backend, which I really hope will get merged soon, with good performance gains, written by Miguel Garcia. Yeah, he finished, but he's on the job market right now. If anybody is interested in a brilliant backend engineer, contact him. Okay, so that's all I had. Thank you very much. I hope you enjoyed it.